welcome back. And please excuse the gravelly voice. My allergies are kicking my butt. But we're going to soldier on here. Today we're going to take a look at the MFJ 916B duplexer or diplexer, depending on who you're talking to. MFJ calls it a duplexer. And I guess it could be called a duplexer of sorts. To me, a duplexer is what you have at a repeater site that separates the transmit and receive frequencies, and a diplexer is used to separate two different bands, but so be it. Duplexer, diplexer, you can use them interchangeably as far as I'm concerned, I guess. And we'll be running some tests on it. We're going to use my VNA UHF by Array Solutions, and I'm sure all the equipment snobs are rolling over in their graves right now going, "Ooh, that's a consumer unit." Well, this consumer unit costs about $1,000, and it compares very favorably with my venerable old 8924C, as well as my somewhat newer, but not brand new, my somewhat newer 8594E Hewlett-Packard. They agree within better than a dB of each other with the UNA VHF, which is good enough for amateur radio as far as I'm concerned. The reason we're going to be using this is I can grab screenshots from the computer over here and edit them into the video, because trying to do that with the camera on the laptop screen and talk and point and do everything else is going to be pretty tough to do. First thing I noticed when I bought this was it's an extremely robust unit. You could literally drive over this with the car. If you dropped it in the driveway and drove over it with the car, I don't think you'd hurt it one bit. It weighs a full solid half a pound. It is in a die-cast aluminum box, and is just indestructible. Now, I've had some people ask me about, I did a review on this on QRZ, and some people dropped me a note and asked me if they could use this outside. Not as is. If you want to put it in some kind of weather-tight enclosure or put a rain cover over it, you could use it. But it is not watertight in any fashion whatsoever. And that means we can open it up and take a look inside, and even repair it if we blew the thing up. So let me get the screws out. Okay, we've removed the bottom cover, and as you can see, looking inside the unit, there's a fairly robust printed circuit board in here. But what would worry me about running a great amount of power is these tiny little ceramic capacitors. There's two of them in here. Those don't look like they're rated for very high voltage. I wouldn't give them more than, I don't know, a couple hundred volts maybe. The other thing of concern is this connection right here. The center conductor from the SO239 on this end is just basically, they put a big glob of solder in here and just caught the edge of the threads. And it seems to me if a coax is inserted and pulled out over time, this is going to work and fracture that solder. Where I have it, it's in a well-protected environment. It's going to be fine. The gauge of the wire in here appears to be probably 16 gauge, heavy enough to handle any amount of power that this unit is designed to take, and should work out well. Actually, it does work out well. Not should, it does work well. So I can't badmouth the construction too much, other than that solder connection. They could have done something a little bit better there. They could have put a little piece, L-shaped piece of sheet metal or brass or something to make that connection and solder it in, but so be it. They're making it down to a cost, and I get that. So let's take a look at what their specifications say on the web page. We'll move over to the computer here briefly. Okay, now that we're over here back at the main computer, please excuse the audio. This is one of those USB headsets, and it's the only thing I can seem to get PowerDirector to recognize. It won't recognize the microphone input for my sound card. It recognizes the line input, but it doesn't recognize the microphone input for some reason. It will work occasionally, and then next time I'll try and it won't, and I've given up. I think I'm going to try building a preamp and use my Heil mic on the line inside, but at any rate, I digress. Here is MFJ's website for the 916B, and It's $24.95, which I think is a very reasonable price, and it comes in 3 different versions. The 916B, which I have, which has 3 SO239s. There's a BN, which has 3 N connectors, female N connectors. And then there's the 916BC, and that has pigtails on 2 of the leads with the PL259s and an SO239 input. Myself, I prefer the flexibility of having the SO239s where I can put any length cable and any combination of cabling I want, but that's my personal preference. Here they rated at 200 watts, insertion loss of 0.2 dB, VISWAR less than 1.2 to 1, and an isolation of 55 dB, and of course 50 ohms impedance. Now things get strange. If we go up here to the downloads and take a look at the documentation that's provided with the unit, this tells us the same 0.2 dB insertion loss, the same 1.2 to 1 VISWAR. This, however, says 60 dB of isolation versus 55, which is on the main page. It tells us 500 watts up to 35 megahertz instead of the 200 watts. It tells us 300 watts all the way up from 50 to 540. Well, you've seen the capacitors that are inside of there. I would be conservative and probably stick with the 200 watt level. So now that we've seen what MFJ claims, 0.2 dB insertion loss, 1.2 to 1 VISWAR, 60 dB of isolation, let's take a look at this thing on the bench and see what kind of numbers we can run. Alright, for our little experiment, I'm going to put a couple of commercially made dummy loads on the 2 ports to emulate or simulate a 2 meter and a 70 centimeter antenna. Now this may look a little kludgy, but these actually have a very good VSWR. These are commercial units, high-end units. I have tried making up my own using PL259s and putting non-inductive resistors in there, and even though my lead length is well under 3/16 of an inch at worst, and in one case on this end it's nearly on the body of the resistor. I've tried several resistors, different types. The best I can do is up to about 200 or 250 megahertz before the VISWAR starts to climb with these. Up around 70 centimeters, they're about 1.8, 1.9 to 1. They starts climbing, and they just weren't working out well. So while this isn't pretty, I know these are good, well up to a gigahertz. Actually, I think this one's up to 6 gigahertz, and this one's good up to 3 gigahertz. And even though it looks a little kludgy, the VISWAR on them is very good. And that's borne out in our test. So I'm going to connect up the network analyzer here, and we're going to run a sweep, and I'll run it from 1 megahertz up to 540 megahertz, and then we'll throw that scan up on the screen and take a look. We'll analyze what we have. So I'm going to come over here, and give me just a second to set up the parameters. Alright, we've run our scan from 1 megahertz to 600 megahertz, and I'll throw this up on the computer screen and identify what the markers are and what the values are. Okay, here we have the SWR sweep of the full spectrum of the unit from 1 megahertz up to 600 megahertz. And this first marker right here is at the top end of the 6 meter band. So you've got the HF band all along here to the top of the 6 meter band. The red line is SWR, the green line is impedance magnitude, and the violet or lavender line here is impedance phase, whether it's reactive, whether it's inductive or capacitive reactance. Those aren't important. What we're looking at right here now is the SWR. This dotted bluish or teal line is the 1.5 to 1 VISWAR point. And you can see down here at HF it's extremely low, basically 1 to 1, all the way up to 6 meters. This line right here represents the center of the 2 meter band, and I didn't put in the start and finish. It's only 4 megahertz wide, and at this span they would have been right on top of one another. At 2 meters and 146 megahertz, we have a 1.213 VSWR. Now, there's going to be discrepancies in my cabling, discrepancies in the dummy loads with the adapters, yada yada yada. That's close enough to 1.2 to 1 for me to say, okay, MFJ is on the money with their VSWR at that point. However, take a look at what happens here at 220. At the beginning of 222 and ending at 225, this unit is unusable. We have a VSWR of basically 4 to 1 here and 5.3 to 1 here. Now MFJ claims this is usable at 220, and obviously it's not. Now either I have a bad unit or this is just the way they are. There's manufacturing differences unit to unit. If MFJ wants to send me another one to review, I would be more than happy to do so, but my unit's unusable at 220. I didn't buy it for 220, I bought it for 2 meters and 70 centimeters, so I kept the unit. I'm perfectly happy with its performance at both 2 meters and 70 centimeters. But as you can see, with this kind of VSWR, you certainly wouldn't want to run it. And here's what I mean about the two of them being close together. There's supposed to be a 3 here. This is marker 3, this is marker 4, but if you put them too close together, the numbers just wipe themselves out. If I'd have tried that at 2 meters over here, you wouldn't have been able to read anything. If I spread this spectrum out, let's say I just put the 2 meter band across here, there'd be plenty of room. But when you're trying to squeeze everything in, there just isn't enough. Anyway, let's move on. We come up here to the 70 centimeter segment, and the 70 centimeter band is fairly wide, so there's plenty of room for 3 markers. And at the beginning of the band, we have 1.28, and right in the middle, and you can see there's a little rise right in the middle, it's 1.32. That's perfectly fine with me. And at the end, it's 1.3. I consider all 3 of those numbers acceptable. And the discrepancy between the 1.2 to 1 that they claim and the 1.3 we're seeing here could merely be those adapters I have on my dummy loads. That's less than optimal, but certainly good enough for our test. So I proclaim that the unit is fine SWR wise. Now we'll go back over to the bench and we'll take a look at the insertion loss. Now we're going to do the insertion loss test. We'll start with the 70 centimeter side. We come out of the vector network analyzer and into the common on the duplexer and out on the antenna port for 432, back into port B here, and we'll look at the S21 parameters. We've done it. We've run a scan. It's up on the screen. I'll make a screenshot of that, and then I'll do the 2 meter side, and we'll go over to the other computer and take a look. Okay, and here we have the 432 port. As expected, the low end of the band is completely rolled off. All we're interested in this, we're looking at the 70 centimeter port. 5, 6, and 7. At marker number 5, way up at the CW end of the band, it says 0.45 dB insertion loss. Center of the band, 0.18 insertion loss, and way up at the high end, 0.26 dB of insertion loss. Now if you take a look, most of this is flat until it gets right here at the end and it steps down, and that's where our 0.45 dB is. So essentially the band is flat, and I will not dispute their claim of 0.2 dB insertion loss. This is so far down into the noise level of this system that I tend to believe that they are getting a 0.2 dB insertion loss. Let's take a look at the 2 meter portion of this and see how it stands up. And just as we had on the 432 side, it rolled off on the HF side. Now that we're on the HF to 2 meter side, the VHF, or excuse me, the UHF side is rolled off. Basically from HF up through 2 meters, 0.1 dB loss. Just very, very good performance. We get up to the 2 meter band, 0.2 dB of loss. Then we hit the 220 section, and as expected, almost 4 dB of loss at the beginning of the band here, and 5.5 dB of loss here. So certainly not usable or not acceptable for 220. But for HF through 2 meters, excellent performance. Now let's take a look at the isolation from port to port. Okay, and here we have the plot of the isolation between the two ports, the VHF side and the UHF side. And the way we did this is we feed the vector network analyzer output into the VHF port and take a reading on the UHF port. Now I did it in both directions because I know somebody's going to ask me that question. By swapping the two cables around, I took a reading in both directions and compared the sweeps. And of course the common terminal at this point is terminated into 50 ohms. This point right here is the only place that changed when I swapped the input and output cables between the two ports. And this is actually the worst case scenario. Right at the 2 meter segment, our isolation, as you can see, right here we go. Sorry. Our isolation is minus 75 dB. So in other words, it's 75 dB down from the reference signal. When I swapped the two ports, this point dropped down to about 80 dB. So the notch here was just a little bit deeper. 75 dB exceeds by a great deal their isolation, claimed isolation of 55 to 60 dB. Over here at the 70 centimeter section, we have 54, 53, 53. Again, I'm not going to dispute their 55 dB claim based on the cables that I'm using and the dummy loads that I'm using, yada yada. As far as I'm concerned, they're close enough to specification. That 2 dB difference is noise with my test setup. This unit meets specification for isolation between the ports, except of course on 220. And again, we'd expect that. This unit has dismal performance on 220. So now let's take this thing out to the vehicle. We'll sweep the two antennas. We'll sweep the 70 centimeter antenna. We'll sweep the 2 meter antenna. Take a look at those results so we know what our baseline is. Then we'll sweep the unit for SWR with both antennas attached and see how it compares with the actual individual antenna sweeps. Okay, and here's our outside setup on my somewhat dirty car on a cloudy day, and you can hear the chipmunks are pretty annoyed with me. They're chirping away in the background. I'm out in their territory and they're not happy about it. The 2 meter antenna is a trunk lid mount, as you can see right there, and the 70 centimeter antenna is up on the roof of the vehicle here. It's a mag mount, but it's got a pretty good viswar. It works out pretty well up there. And down here on the back of the vehicle we have our 6 meter antenna. All of this running, of course, off my 706 Mark II-G. Down here, oops, sorry about the fast pan, we have the laptop computer and the network analyzer, and we have an extension cable which has been normalized out at the end using standard loads, open and short, just like you would do at the port of the network analyzer. And we've compensated for the cable length by normalizing it out at the end. So now we'll check the antennas. And here's the sweep of the 2 meter antenna mounted on the trunk lid lip. And from about here to here, where almost all of my FM repeater operation is going to take place, we're below 1.5 to 1, and in fact where the marker is, it's 1.28 to 1. And it does tend to rise down here in this end of the band where the weak signal and CW activity takes care of. But this is the band segment I'm interested in when I'm mobile. And you can see the antenna by itself, just the, no duplexer at this point, just the antenna, is about 1.2 to 1 where the marker is. Now let's take a look at the 70 centimeter antenna. And here we have the 70 centimeter antenna swept from one end of the band to the other here. And it's pretty good, 1.5 to 1 here. We get a little bobble in the center where it goes high, and then it dips below 1.5 to 1 here. So we cover most of the FM repeater inputs and outputs with no issues. And this is just going to be as a comparison, so when we have the diplexer or duplexer in line with both antennas connected, we'll be able to run a comparison and see if there's any interaction. So let's remember 1.5 to 1, or 1.51 in the center. How's that? That'll be an easy number. So let's hook the diplexer or duplexer up and take a look. Okay, here we have our combined sweep with the two antennas and the duplexer in line. Again, everything is still mounted in the trunk, so there's no interaction between the analyzer and the antennas. Now we have a whole lot of crazy SWR stuff going on here. That's because we only have a 2-meter antenna here, and we have a 70-centimeter antenna here. And if we had a dummy load, this of course would have been flat, but since we now have nothing that's of 50 ohms impedance in this range, you're going to get all kinds of crazy stuff going on, and this just happens to be some resonance in the system, length of cables versus there's so many factors that come into play here. Something is resonant at this point and showing a 50 ohm impedance, but this is not real. This is an artifact, if you will. Over here we have the 2-meter section. We'll blow that up in a minute and look at it. Over here is the 70-centimeter section, and it looks like we have a new little bump here, probably due to the interaction between the cables and the antennas and so on and so forth. We'll spread both of these out, but you can see overall that the two areas of interest are showing up and looking like they have a fairly decent VSWR. Let's take a look at the 2-meter antenna now that it's connected into the system, and the 70-centimeter antenna. And here is the SWR sweep through the duplexer of the 2-meter antenna, and you can see the shape, overall shape of that dip is pretty much the same. We'll move in the original trace here, and without the combined antennas in the system, you can see the SWR is a little bit better. However, if we move this one back up out of the way, we're still, for the most part, through the FM band 1.5 to 1. Actually, according to this, it's 1.504 to 1. So close enough. That will work. I'm happy with that result. Now let's take a look at the 70-centimeter antenna segment in the combined suite. And last but not least, here's the 70-centimeter antenna combined with the 2-meter antenna and the duplexer. And as we saw in the full span sweep of the two of them combined, there is a little bit more of a bump down here on the very high end of 70 centimeters. And just to show you what it used to look like, you can see right here it did not exceed 2 to 1. Now ignore the fact that these green and purple traces are on here. I shut those off for the latter scans. These are just phase angle and phase intensity. We're not concerned with those. All we're concerned with this. So right here in the center, it's 1.51, and if I grab this guy and get it up out of the way in the center, it's actually gotten better. There's an improvement in the center. It's 1.39 or 1.4 to 1. So we've gained a little bit of a bump on the end. This has jumped up to 2.09, and previously, if I look up at the other screen, it was 2.02. So a little bit of an increase right here. A little bit of a decrease in the center, and pretty much unchanged here. This was 1.66 and now it's 1.72, so virtually no difference. I'll bet if I ran 3, 4, 5 sweeps, you'd see discrepancies of a couple tenths of a dB, especially since I have a 500 kilohertz span rate, so things, it jumps from one to the next to the next to the next in 500 kilohertz steps. I could smooth that out. For what I'm doing, it's not needed. So there you have it. The MFJ unit works fairly well if you're interested in 2 meters and 70 centimeters, running 2 antennas from a single output or 2 radios into a single antenna. It'll do the job nicely. Again, I wouldn't exceed the 200 watt level with it, but for the price, for your $25, you get a fairly decent unit. Hope you found this interesting or helpful or informative. If you did, please give it a thumbs up. Give us a subscription. The more subscriptions we get, the more encouraged we are to do more of these types of reviews and tests. Thanks for stopping by. As always, I'm the Radio Mechanic. See you later.